Somewhere in the layers of ancient rock, beneath cities and deserts and forgotten oceans, lie the bones of monsters stranger than fiction. Creatures with sails on their backs, claws longer than swords, jaws that could crush bone in seconds. And yet, they were real. Dinosaurs ruled the Earth for over 160 million years. So long, it makes the entire existence of humans feel like the blink of an eye. But here's the weird part. Despite all our fossil digs, research papers, and museum exhibits, we still barely understand them. What did a T-Rex really sound like? How fast could raptors run? Why did some dinosaurs have feathers? And were they really the ancestors of modern birds? And perhaps the biggest mystery of all, how did such titans simply vanish? Tonight, we're going to dig deeper than ever before. Not just into the facts, but into the stories, the science, and the latest mind-blowing discoveries that are rewriting everything we thought we knew about dinosaurs. So whether you're here to learn, or just drift off into dreams of prehistoric worlds, get ready to see dinosaurs as you've never seen them before. If you're already hooked, and honestly, how could you not be? Go ahead and give this video a thumbs up. Hit that subscribe button to unearth more deep dive documentaries like this one. And if you've got that one dinosaur-obsessed friend, we all do, go ahead and share this their way. Let's keep the wonder alive, one fossil at a time. There is something strangely magical about the time before dinosaurs, a forgotten era that gets only a footnote in most documentaries. Yet, this ancient chapter of Earth's history is where the foundations were laid, geologically, biologically, and atmospherically, so for one of the most awe-inspiring ages our planet has ever seen. Think of it this way. If Earth's 4.5 billion year history were compressed into a single 24-hour day, the dinosaurs wouldn't appear until late evening. So, what happened in the hours before that, in the morning, afternoon, and early evening of deep time? Well, a lot more than you'd think. Let's rewind the clock. Way back. Part 1. Earth's violent childhood. Think the Age of Dinosaurs was harsh. Try imagining a planet still being bombarded by space rocks, shaking from constant volcanic eruptions, and wrapped in a poisonous atmosphere you wouldn't survive in for more than a breath. This was the Hadean Eon over 4 billion years ago. Or, Earth was molten. There weren't any oceans yet, just lava seas and an atmosphere thick with carbon dioxide and methane. But somehow, from this chaos, the seeds of life started to form. It's kind of mind-blowing, right? In an environment so hostile, something began to stir on a microscopic level. Simple molecules collided, combined, and evolved. By the time we hit the Archean Eon, early bacteria had started turning sunlight into sugars, the first photosynthesizers, slowly filling the air with oxygen, and that changed everything. As oxygen levels rose, Earth was set up for a biological revolution. It just took a few billion years. Part 2. The Cambrian Explosion, Life Goes Wild. Fast forward to about 541 million years ago, and the gears really start turning. Welcome to the Cambrian period, one of the most important biological booms in Earth's history. In just a few million years, a blink in geologic time, nearly every major animal group appeared. Creatures developed eyes, legs, armor, and even primitive brains. The oceans swarmed with bizarre life forms we'd struggle to recognize today. One of the strangest, Opabenia, a five-eyed, backward-swimming anomaly with a vacuum-like proboscis coming out of its head. More science fiction than science. And yet these early life experiments were laying the groundwork for future ecosystems, crawling, swimming, and even burrowing life that would eventually adapt to land. Ask yourself, what would the world look like if the Cambrian creatures had remained dominant? Would we ever have gotten dinosaurs? Unlikely. As weird as it may sound, the path to T-Rex starts with shrimp-like arthropods and jelly-brained sea worms. Part 3. Colonizing the land. For most of Earth's history, staying in the sea had been smart. It was stable, full of nutrients, and protective from harsh UV rays. But around 430 million years ago, things began to change. Land was calling. Thanks to those oxygen-producing bacteria and plants, Earth's atmosphere had grown more breathable. Mosses and ferns spread onto shorelines. Soon insects appeared, some massive by today's standards. In the Carboniferous period, dragonflies could have wingspans of over 2 feet. Why so big? One theory ties it to high oxygen levels, possibly over 30% compared to 21% today. Imagine breathing supercharged air, muscles working better, wings flapping faster, bodies evolving bigger. Meanwhile, vertebrates were making their own move. From fish-like creatures came tetrapods, the first animals to crawl out of the water and walk on land with limbs. These weren't dinosaurs, yet. But they were something just as crucial. Their ancestors. Part 4. The True Monsters of Prehistory. Now picture a swampy world buzzing with giant insects, dense forests, steaming heat, and a group of animals beginning to dominate. Synapsids. You might not recognize the name, but synapsids were the dominant land vertebrates of the Permian period, well before dinosaurs appeared. Some looked like reptilian tanks. Others, like Dimetrodon, with its massive sailback, have often been mistaken for dinosaurs in pop culture. Ironically, Dimetrodon is more closely related to us than to any dinosaur. See, synapsids are part of the evolutionary line that led to mammals, and for millions of years it looked like they were here to stay. But then, something catastrophic happened. Part 5. The Great Dying. Roughly 252 million years ago, the world suffered the most devastating extinction in its entire history, the Permian-Triassic extinction event, known chillingly as the Great Dying. We're talking 96% of marine species, 70% of land vertebrates, and almost all plant life gone. The trigger? Still debated, but the strongest contenders include massive supervolcano eruptions in what is now Siberia, huge spikes in atmospheric CO2, ocean acidification and deoxygenation, a possible methane release that drove rapid warming. Whatever caused it, life on Earth came dangerously close to ending completely. But extinction creates opportunity. With most niches empty and ecosystems in ruin, the survivors had a blank canvas. And among them were a few small archosaurs, a group of reptiles that, in the shadows of this catastrophe, would quietly evolve into the icons of prehistory, dinosaurs. But that next chapter in the planet's story, it's not about destruction, it's about rebirth. And what came next was nothing short of astonishing. Chapter 2. The Dawn of the Dinosaurs. The world was quiet. After the Great Dying, it wasn't just the creatures that had disappeared. Entire ecosystems had unraveled. Plants struggled to regrow. Deserts stretched across continents. For millions of years, the Earth was healing. Slowly. But beneath this silence, life hadn't given up. It was gathering its strength, evolving, preparing for a new age. And in the shadows of extinction, something unexpected began to stir. Something small, fast, and unlike anything that had come before. This is the unlikely origin story of the dinosaurs. Part 1. Survivors in a Scarred World. Let's set the scene. It's the early Triassic period, about 250 million years ago. Earth is brutally hot. Temperatures in some areas may have soared past 120 degrees Fahrenheit. Rainforests have collapsed. Oceans are oxygen-starved. It's the kind of apocalyptic world where only true survivors stood a chance. And among those survivors were the archosaurs. Now here's where things get interesting. Archosaurs were a broad group of reptiles that included ancestors of crocodiles, pterosaurs, and, yes, dinosaurs. But early on, they weren't the stars of the show. That title still belonged to their relatives. Other reptiles like rhynchosaurs and synapsids, especially creatures like Lystrosaurus, a squat, pig-like beast that somehow made up nearly 90% of all land vertebrates after the extinction. The dinosaurs? At this point, they were barely a whisper in nature's script, small light-bodied reptiles scurrying through the underbrush. Not exactly king-of-the-world material, yet. Part 2. the rise of the archosaurs. As the Triassic rolled on, Earth slowly began to green again. Forests returned, rivers carved new paths, and evolution kicked into high gear. The archosaurs began to branch out. Over time, they formed two major lineages. One, the Pseudosuchians, ancestors of modern-day crocodiles. Two, the Ornithodyrans, a group that would eventually give the world pterosaurs and dinosaurs. Why did the Ornithodyrans succeed while so many others didn't? A few reasons stand out. Firstly, posture. Unlike the sprawling limbs of lizards or early reptiles, the ancestors of dinosaurs evolved to stand upright, with legs directly beneath their bodies. This gave them speed, endurance, and agility, a massive advantage in a landscape still recovering from mass extinction. Secondly, they were likely warm-blooded, or at least somewhere in between cold and warm-blooded. That meant more energy, faster growth, and better resilience in cooling climates. And third, let's be honest, luck. A second extinction event, known as the Carnian pluvial event, occurred around 233 million years ago. Marked by sudden rainfall and climate swings, it wiped out large swaths of competing species. Guess who survived? Yep, dinosaurs. Part 3. The first true dinosaurs. So when do we officially get our first dinosaurs? That's a tougher question than it sounds. The earliest definitive dinosaurs appear roughly 230 million years ago, during the late Triassic. But new discoveries constantly push those dates earlier. Fossils found in Argentina and Brazil, in places like the Ixigualasto Formation, are giving us tantalizing glimpses into these original dino pioneers. Meet Eoraptor, a small, slender, two-legged creature, possibly an early theropod. Big eyes, light body, more gazelle than monster. Herrerasaurus, a predator, fast and strong-jawed, growing up to 20 feet long, possibly among the first real carnivorous dinosaurs. Saturnalia, more closely aligned with early sauropods, hinting at the giant long necks to come. Fascinatingly, all of these early dinosaurs were pretty small, maybe 3 to 20 feet long, weighing just a few hundred pounds. It almost sounds underwhelming, right? But what they lacked in size, they made up for in adaptability. And that, more than anything, would be their superpower. Part 4. Not alone on Earth. Yet here's the thing. Even after dinosaurs appeared, they didn't instantly take over the world. For tens of millions of years, they shared the Earth with other archosaurs, early crocodile relatives, giant amphibians, and even some holdout synapsids still clinging on. This period, the late Triassic, was like nature's testing ground. Species came and went at a furious pace. Entire groups rose and fell within a few million years. Dinosaurs were evolutionary underdogs. They were fast, yes. Efficient, yes. But they still had competition, until another cataclysm changed everything. Sound familiar? This time it was the end of the Triassic, the third mass extinction in our story. Likely triggered by massive volcanic eruptions tied to the breakup of the supercontinent Pangaea, this event wiped out most competitors on land and in the seas. Suddenly, the stage was cleared, and the dinosaurs? They were ready. Part 5. The Quiet Conquest. There's no dramatic battle scene, no single aha moment. Dinosaurs didn't conquer the Earth overnight. They outlasted, adapted, and moved into vacant ecological niches. By the time we reach the early Jurassic period, about 201 million years ago, dinosaurs are everywhere. Herbivores begin growing larger, carnivores diversify. The dino blueprint begins its golden age of experimentation. What started as scurrying forest dwellers had now become the dominant force on land, not because they were born the biggest, but because they were designed to change. And that ability to evolve rapidly, faster than almost any large vertebrate group in history, was about to lead to something Earth had never seen before, a world of giants. But that's a story worthy of its own spotlight. Chapter 3. Dinosaurs take over. The curtains have lifted, the wild, chaotic Triassic is over, and the Earth is stepping into a brand new act. Imagine waking up about 200 million years ago during the early Jurassic period. The Earth's once fractured ecosystems are recovering. Forests are reclaiming the land. Rivers run wild, carving pathways through ancient landscapes teeming with life. And wherever you look, dinosaurs. Not just surviving anymore, but thriving. Small ones, giant ones, armored, horned, long-necked, sharp-toothed, clawed. It's like evolution turned the dial up to 11 and let nature play. This is the moment dinosaurs go from interesting creatures to global conquerors. Ever wonder how it happened? Let's unpack it. First, a little geography lesson, one with massive consequences. Back in the early Jurassic, the entire land surface of Earth was mostly one massive continent, Pangaea. Picture it like one mega blob of rock stretching from pole to pole. No Atlantic Ocean, no separate Americas, Europe or Africa. Just vast land masses connected seamlessly. And for dinosaurs, that was a dream come true. This meant herbivorous species could roam thousands of miles, spreading and adapting to different climates. Carnivores could follow the food wherever it went. Evolution didn't happen in isolated pockets. It spread fast, like wildfire. So, when dinosaurs started radiating into different types, the effects were global. Let's pause for a moment. Why were dinosaurs so successful? What gave them the edge, biologically, over all the other reptilian groups? It really boils down to a few incredible adaptations. 1. Upright posture. Unlike earlier reptiles that walked with their legs sprawling out to the sides, dinosaurs' legs tucked directly underneath their bodies. This gave them greater endurance, longer strides, and allowed for surprising speed even in massive species. It's kind of like comparing a lizard crawl to a cheetah sprint. 2. Hollow bones. Yes, many dinosaurs had hollow bones, a trait that lightened their skeletons without sacrificing strength. This made them more agile and later helped pave the way for flight. 3. Rapid growth. Many dinosaurs grew remarkably quickly. Fossilized bone rings, kind of like tree rings, show that they could go from hatchling to adult in just a few years, allowing populations to bounce back fast from trouble. 4. Advanced lungs and efficient movement. The structure of some dinosaurs' hips and lungs reveals surprising metabolic abilities. Some may have been warm-blooded or close to it, giving them an enormous edge in colder regions or variable climates. In other words, dinosaurs weren't just strong, they were versatile. And that, more than any single superpower, made them unstoppable. Now we truly begin the age of experimentation. As Earth rolled into the middle and late Jurassic, dinosaurs began exploring many different evolutionary paths, and they didn't hold back. Start with the sauropods, the long-necked giants. Species like Apatosaurus, Diplodocus, and Brachiosaurus stretched taller than trees and weighed more than commercial airplanes. Yet these weren't mindless brutes. Their small heads and gigantic digestive systems allowed them to process enormous amounts of plant material, essential in a land with fierce competition for food. And how did they defend themselves? Well, sometimes they didn't need to. When you're 80 feet long and weigh over 40 tons, not many predators even bother. But evolution didn't stop there. Over on the meat-eating side, we see the rise of the theropods, a group that includes all the classic bipedal predators, from Allosaurus to, eventually, T-Rex. These early carnivores were fast, smart, and well-equipped with claws, keen eyesight, and serrated teeth. They weren't just lumbering hunters, they were adaptive killing machines. Need something smaller? No problem. Herbivorous groups like ornithopods began to thrive. These were the multitaskers of the dinosaur world, nimble, social, and some even capable of running on 2 or 4 legs. Think, the ancient ancestors of Iguanodon or Hypsilophodon. In short, every ecological niche began to fill. Grazers, stalkers, scavengers, ambushers, herd travelers, nomads, diggers. And the more diverse they became, the more unstoppable the dino dynasty seemed. Of course, success breeds conflict. As plant eaters grew larger, tougher, and more armored, carnivores evolved to become smarter, faster, and more coordinated. It sparked one of nature's great evolutionary arms races, a back and forth of adaptation fed by survival pressure. Sauropods grew enormous, possibly traveling in herds to shield their young. Meanwhile, predators began developing tactics, perhaps even hunting in packs. Scientists still debate whether predators like Allosaurus collaborated during a kill, or scavenged independently. The fossil record offers clues but little certainty. What's clearer? Each adaptation in weaponry, like tail clubs, bony frills, or razor-sharp claws, was met with a counter-adaptation. It wasn't just who was stronger, it was who was smarter, faster, more evolved, and the dinosaurs were playing the game better than anyone. Now here's where science starts tugging at the imagination. For decades, we pictured dinosaurs as slow, scaly, cold-blooded monsters. Thanks in part to early pop culture and outdated fossil interpretations, they were often drawn as green, drab, almost sluggish beasts. But recent discoveries have shattered that image. Feathers on theropods, yup, vibrant color patterns, possibly for show. Strong evidence, nests, migration, even potential parental care, all likely. Dinosaurs weren't slow-motion monsters. They were dynamic, alert, and brilliantly adapted. Imagine a small raptor species with iridescent feathers glinting in the sun, darting between trees, or enormous sauropods shaking the ground as they communicate through low-frequency rumbles we can't even hear today. Our modern vision of the Mesozoic is no longer a swampy slog of tail-dragging lizards. It's a thriving biosphere full of drama, movement, and color. And the best part? The fossil record is still full of secrets. Every new dig has the potential to rewrite the story of these creatures all over again. By the middle of the Jurassic, dinosaurs weren't just surviving, they were shaping the very ecosystems they lived in. Their rise wasn't just about dominance, it was about becoming essential to Earth's biome. From the tallest point of a giant's back to the sharpest tip of a predator's claw, every dinosaur had a role to play. And in the coming chapters, these roles would grow even more complex. Because as the Jurassic gives way to the Cretaceous, dinosaurs don't fade out. They evolve even further. They learn to fly. They grow armor. They sprout horns. They give us the icons. And what comes next? You've probably seen some of them in museums, textbooks, even movies. But trust us, the full story is way better than fiction. Chapter 4. Titans of the Jurassic. By the time the Jurassic roared into full swing, around 170 million years ago, the Age of Dinosaurs had become officially epic. It's one thing to evolve and thrive. It's another to dominate every landmass on Earth, from steaming equatorial forests to wind-blown floodplains. And in this chapter of history, dinosaurs weren't just thriving, they were going big. Truly, unimaginably big. When most people picture dinosaurs, this is probably the version they see. Towering, long-necked giants casting shadows over everything in sight. Herds of armored beasts trudging through misty valleys. Predators with teeth like steak knives stalking prehistoric prairies. This was the age of the Titans, and if you think you know these creatures already, just wait. Let's start with a simple question. Why did dinosaurs grow so massive? It's tempting to shrug and say, because they could. But the reality involves a beautiful blend of biology and environment. The Jurassic world was warm and stable, no polar ice caps, high oxygen levels, and most importantly, vast supplies of vegetation. Gigantic conifers, ferns, and cycads blanketed the landscape, supplying an all-you-can-eat buffet for any creature tall enough to reach it. And few dinos could rival the sauropods, those long-necked, whip-tailed marvels that remain the largest land animals to ever walk the Earth. Take Brachiosaurus, for example, the giraffe of the dinosaur world, except far, far bigger. Brachiosaurus stood up to 40 feet tall and weighed around 40 metric tons, potentially more. Unlike most sauropods, its front legs were longer than the rear, giving it a steeply sloped posture, perfect for plucking leaves from the very tops of trees. Then there's Diplodocus, graceful, long-bodied, and pushing lengths of 90 feet or more. Its tail alone could stretch longer than a semi-truck, whipping through the air, possibly fast enough to crack like a bullwhip. And we haven't even reached the true giants like Argentinosaurus or Patagoteton, which come much later. But the Jurassic period laid the blueprint. These weren't monsters. They were ecosystem engineers, shaping the land with every stomp and graze. Their daily lives sculpted the environment, and naturally something had to hunt them. Where there are giants, there are giant predators. But before we meet a certain infamous monster from the Cretaceous, T-Rex, we're looking at you, The Jurassic had its own top-tier killer, Allosaurus. Sleeker and more nimble than T-Rex, Allosaurus was no less deadly. Picture a 30-foot-long predator with blade-like teeth and claws made for slashing, not crushing. Its skull was lighter than its size suggests, allowing for quick movements, and its jaws could open wide enough to hook pieces of meat out like a vulture. It's possible Allosaurus didn't hunt alone. Some fossil sites show clusters of individuals near large herbivore remains, hinting at either group hunting or feeding frenzies. But it wasn't the only threat skulking around. You had carnivorous dinosaurs like Ceratosaurus, with distinctive nose horns and a deep, powerful skull. Others, like Megalosaurus, were among the earliest predatory dinosaurs known to science, literally the first dinosaur ever named in history. And while these meat-eaters were impressive, they weren't always the biggest in their ecosystem, not with 30-ton armored sauropods stomping around. That pushed predators to evolve smarter hunting strategies, speedier frames, and specialization. The prey got bigger, the hunters got cleverer. Nature kept upping the stakes. Not every dinosaur needed to be massive to be marvelous. Some went a different route. They evolved armor. Enter the stegosaurs, perhaps the most visually distinctive dinosaurs ever to walk the earth. You probably know Stegosaurus by its iconic backplates and that gnarly spiked tail called a thagomizer. Yes, that's its real informal name, coined in a cartoon and accepted by paleontologists ever since. Stegosaurus had a brain about the size of a walnut. No offense, Stego, but don't let that fool you. It had simple defenses, but they were absurdly effective. Rear up, swing that tail, and even a full-grown predator could be in serious trouble. And those plates? They may have helped with thermoregulation, possibly even display. Picture a herd of stegos roaming the plains, plates glowing different hues for signaling. Science can't confirm the coloration, but newer modeling hints they weren't just big lumps of bone. They may have been dynamic display tools. A walking tank with style. Nature doesn't mess around. This era wasn't all giants and killers. The Jurassic was home to a rich tapestry of animals, many of which played key ecological roles just as important as the headliners. Take the ornithopods, small to medium-sized herbivorous dinosaurs that were fast, adaptive, and abundantly successful. Species like Camptosaurus were early experiments in this lineage, later giving rise to famed dinosaurs like Iguanodon in the Cretaceous. Then you had early versions of ankylosaurs, ancestors of even more heavily armored dinosaurs still to come. Imagine low-slung tank-like bodies covered in bony plates from snout to tail. There were also the Dryosaurs and Hypsilophodonts, lightweight browsers with strong legs and sharper wits than you'd expect. Think prehistoric gazelles in both function and form. They kept the food chain alive. They were prey, yes, but also grass trimmers, seed dispersers, and tenders of the prehistoric garden. Without them, the dynasty of dinosaurs might have collapsed under its own weight. The Jurassic wasn't just biologically dynamic, it was geologically alive. Pangaea, the supercontinent we mentioned earlier, began to break apart during this time. The land literally cracked, drifted, and tore itself away toward new formations. New oceans formed in the gaps. Coastal regions expanded, environments diversified, and dinosaurs adapted to it all. As islands formed, some species became isolated, evolving exaggerated features or shrinking into dwarfed variants. Classic island evolution in action. Meanwhile, new mountain ranges and volcanic activity restructured migration patterns. Watering holes changed, forests moved. Through it all, dinosaurs not only adapted, they throve. It's easy to forget they did all this without technology, tools, or civilization. Yet they ruled Earth far longer than humans have existed. By the end of the Jurassic, dinosaurs had already clocked tens of millions of years at the top. To put that in perspective, if dinosaurs had Apple Watches, they would have been measuring time in epochs, not calendar years. That longevity, it wasn't a fluke, it was earned. Generation by generation. Chapter 5. Rulers, Predators, and Pack Hunters. By the time the Cretaceous period takes over, around 145 million years ago, the world of the dinosaurs is at its most evolved. The continents are separating, sea levels are rising, climate zones are diversifying. What this means for dinosaurs: opportunity, new ecosystems, new challenges, and new rivals. And while herbivores continued to innovate with armor, size, and social complexity, the predators, they did what predators do best. They adapted, specialized, and in many cases, got terrifyingly smart. This chapter is a showcase, not just of the biggest or the most violent, but of the most effective killers in Earth's history, and the cunning strategies they may have used to stay at the top. Spoiler, it's not always about size. Let's just go ahead and address the superstar, Tyrannosaurus rex. Roughly 66 million years ago, in the late Cretaceous, a 40-foot, 9-ton apex predator roamed what's now North America. Its skull, over 5 feet long. Its bite force, stronger than any land animal alive or extinct, more than 12,000 pounds per square inch. It could crush bone like it was snapping celery. And yet, despite its pop culture fame, we're still arguing basic facts about T-Rex. Was it a lone hunter or a scavenger? Did it sprint after prey or simply overpower slower targets? Here's what we do know. Its olfactory bulbs, the part of the brain devoted to smell, and were enormous. This was likely a creature that could sense a meal from miles away. Whether that meal was fresh or rotting didn't matter. Latest findings suggest T-Rex was likely both a hunter and scavenger, doing whatever it needed to survive. Why choose? But even a king has challenges. T-Rex was the alpha of its time, but not necessarily the biggest predator ever. Over in what's now Africa, millions of years earlier, something else reigned: Spinosaurus. Measured at up to 50-59 feet long, it was longer than T-Rex, with a crocodile-like skull and a huge sail on its back. For a long time, it was thought to be a bipedal predator, like other theropods. But recent discoveries have flipped the Spinosaurus story entirely. Turns out, this giant may have been semi-aquatic, the first known dinosaur to fully adapt to life in the water. Slender hind limbs, dense bones for buoyancy control, a powerful tail shaped for swimming. Spinosaurus likely hunted fish lurking in rivers and mangrove swamps like a prehistoric river monster straight from myth. And just like that, our image of dinosaurs expands, from land to sky to waterfront predator. But not all giants were loners, because now we enter the world of pack hunters. It's still one of the most thrilling ideas in paleontology that some dinosaurs, like wolves or lions today, hunted in organized groups. The main candidate? Dromaeosaurs. You've definitely heard of them, only you probably know them by another name, raptors. Let's clear something up first. Hollywood greatly exaggerated their size. The real velociraptor stood about 3 feet tall, think turkey-sized, albeit a very, very angry turkey with a hunting knife on each toe. But other dromaeosaurs, like Utahraptor, grew much larger, up to 20 feet long. Still, size wasn't what made them scary. It was the brain. Compared to body size, raptors had unusually large brains, especially in the forebrain, which processes sensory information and problem-solving. Couple that with keen eyesight, agility, and retractable sickle claws, and you're looking at some of the most advanced predators to ever walk the earth. Many paleontologists believe raptors may have lived in packs, chasing prey together, coordinating moves, and maybe even communicating vocally. Evidence? Bone beds full of multiple individuals, fossils of prey surrounded by raptor teeth. Social behavior traced by tracks. Is the debate settled? Not quite. Behavior doesn't fossilize well, but if true, the Cretaceous saw the rise of not just beasts but brains, predators that began thinking like a team. But brute force wasn't the only strategy on the menu. Cretaceous ecosystems were teeming with predators that took the sneakier route. Take Troodon, once considered the most intelligent non-avian dinosaur due to its large eye sockets and brain-to-body ratio. Troodon may have been nocturnal, using keen night vision to track defenseless prey under cover of darkness. And then there's Oviraptor, whose name, Egg Thief, was a case of unfortunate misunderstanding. When its fossils were found near nests, paleontologists assumed it was stealing eggs. Turns out, it was probably protecting its own. Oops. Still, the name stuck. And the abilities? Impressive. Oviraptors had parrot-like beaks, possibly feathers, and a broad diet that included plants, small animals, and maybe, yes, the occasional stolen snack. Others, like Ornitholestes and Compsognathus, were small, quick, and possibly covered in fuzzy filaments or feathers. Life as one of these mid-tier predators was a constant gamble. Fast attacks, faster retreats, and eating what you could when you could. Fast, wily, adaptive. Even if they weren't the biggest, they absolutely mattered. One of the most remarkable things about Cretaceous predators wasn't just how they hunted, but the roles they played in their ecosystems. Just like modern predators shape the behavior and migration of prey animals, dinosaurs did the same. Large plant eaters like ankylosaurs, triceratops, or hadrosaurs weren't just walking buffets. They evolved sophisticated defenses, largely in response to predator pressure. Ankylosaurs became armored tanks with tail clubs. Ceratopsians developed frills and facial horns. And hadrosaurs, duck-billed dinosaurs, likely moved in large herds, developed strong legs, and grew keen hearing and eyesight to detect threats early. In truth, it was all a feedback loop. As predators evolved smarter strategies, prey evolved sharper senses. As prey traveled in bigger herds, predators had to coordinate better. As defenses grew stronger, hunting pressured innovation. This is how ecosystems build themselves, not in one explosive moment, but across millions of years of competition and co-evolution. And dinosaurs shaped their worlds through survival. Predators aren't just the monsters of the story, they're the balancing force. Without them, herbivore populations might have exploded unchecked. Ecosystems could collapse under their own weight. The rulers of the Cretaceous, whether roaring alone like T-Rex, swarming in raptor packs, or lurking beneath ancient waters like Spinosaurus, weren't just terrifying to look at, they were absolutely vital. They weren't villains, they were architects of the prehistoric world. And some of the most fascinating layers of their story are only just being uncovered. Because in the next chapter, we dive into something even more surprising. There are clues, actual feathers, advanced lungs, and early wings that suggest some dinosaurs were building towards something new, something revolutionary, flight. Evolution wasn't finished, it was just looking skyward. For decades, if you asked anyone to draw a dinosaur, the result was pretty predictable. Big, scaly, maybe green, usually roaring, maybe chasing a jeep or eating a goat. But then, something changed. In the last few decades, paleontology experienced a revolution. Not a slow creeping shift, but a tectonic shakeup that redefined what dinosaurs actually were. Feathers, warm-bloodedness, social dynamics, color, intelligence. What started as strange discoveries in dusty fossil beds led to one major takeaway. Dinosaurs were far more bird-like than we ever imagined. Let that sink in for a second, because if you picture a monstrous, roaring T-Rex stomping through the jungle, you might be picturing it all wrong. Let's explore how cutting-edge science cracked open Jurassic stereotypes and started painting dinosaurs in full color. Ask any kid, did dinosaurs have feathers? 30 years ago, the answer would have been a hard no. Today, it's a resounding yes, and not just for the flying kind. It all started unraveling in the 1990s, when paleontologists working in Liaoning, China, discovered something jaw-dropping: incredibly well-preserved fossils of small theropods with clear traces of feathers. The first major find was Sinosauropteryx, a small predator about the size of a turkey, with visible filamentous structures along its body. At first, some scientists questioned whether those were actually feathers, but then more fossils appeared, and more, and more. Caudipteryx had symmetrical, flightless feathers. Microraptor had wing-like feathers on its arms and legs, 4 wings in total. Dilong, a relative of T-Rex, also showed feather-like structures. The feather train had officially left the station. And the implications were huge, because these weren't just extinct birds. These were non-avian dinosaurs, proving that feathers didn't evolve for flight at all. They likely evolved for insulation, display, or even thermoregulation, millions of years before any creature ever took off. So yes, feathers came before flight. That simple fact blew the whole field wide open. Here's the real kicker, and it's not some fringe idea, it's scientific consensus now. Birds are dinosaurs. Full stop. To be more precise, modern birds are avian dinosaurs, descended directly from small, feathered theropods. That chirping robin in the tree, that chicken on your plate, that falcon soaring overhead, all of them are part of the same evolutionary family tree that includes Velociraptor and even T-Rex. This relationship is supported by skeletal similarities, especially in the wrist, ankle, pelvis, and skull. Air sac respiratory systems. Birds have a unique, hyper-efficient lung setup that turns out to resemble what fossil evidence shows in many theropods. Feathers, obviously, and even nesting behavior and egg structure. In fact, some fossilized oviraptors were found in bird-like positions, hunched over nests, protecting eggs with outstretched arms, just like a brooding mother hen. So yes, the age of dinosaurs didn't end. It flew away. For decades, dinosaurs were thought to be cold-blooded, sluggish brutes that needed warm weather to function. Sound familiar? That idea mostly came from early comparisons to present-day reptiles, lizards, crocs, gators. But in the last few decades, multiple lines of evidence suggest something different. Many dinosaurs, especially theropods and fast herbivores, were likely warm-blooded or at least mesothermic, meaning they fell somewhere between cold and warm-blooded. For instance, growth rings in dinosaur bones show rapid development, similar to warm-blooded animals. Bone structure suggests high activity levels. Feathers? Pretty much a dead giveaway that an animal at least needs to regulate its body heat. Some species even lived in polar environments where cold-blooded creatures wouldn't survive year-round. Warm-bloodedness comes with a cost. It requires a ton of energy, but it allows for more sustained activity, sharper reflexes, and higher intelligence. Sound like the sluggish lizards of old? Not even close. Dinosaurs were in many cases living fast, growing fast, reacting fast. It's a whole new energy level for creatures once thought slow and dumb. Speaking of dumb, let's be fair, we'll never know exactly what a dinosaur was thinking. But if you want to know whether they were capable of higher behaviors, communication, strategy, parental care, the evidence is surprisingly convincing. Some raptors had large brain cases, advanced vision, and even asymmetrical ears, a trait shared with modern owls and hawks that helps them hear directionally. Tracks left by dinosaurs show parallel group movement, potentially indicating social behavior or migratory herds. And don't forget those brooding raptors preserving their eggs. That's more parental instinct than a lot of animals on Earth today can claim. Even duck-billed dinosaurs, long thought fairly basic, had complex skull crests which could possibly resonate sound, acting as trumpeting calls across herds. So sure, we're not saying dinosaurs were holding book clubs or playing poker, but solitary, lumbering brutes, not a chance. They lived in dynamic environments and responded with dynamic behavior. Life demands it, and evolution delivers. Maybe the most exciting twist in dinosaur science is something nobody saw coming. We're starting to uncover what dinosaurs actually look like. Thanks to discoveries like Sinosauropteryx and other ultra-rare feather fossils, scientists have observed melanosomes, microscopic pigment-bearing parts of feathers. By comparing those to modern birds' melanosomes, researchers can start to reconstruct color patterns. The first dinosaur we've ever seen in color, probably Sinosauropteryx, with reddish-brown tones and a striped tail. Think raccoon meets rooster. Other species might have had iridescent feathers like hummingbirds, patterns to attract mates, or camouflage depending on their habitat. Want more? CT scans can now peer inside fossil skulls. Analysis of preserved lung cavities, blood vessel traces, and muscle attachments can tell us how these animals moved, breathed, even vocalized. Could T-Rex have roared? Maybe not how you think. Some scientists suggest low-frequency rumbles, more like crocodilian booms or deep bass moans, the kind you feel in your chest before you even heard it. And birds? They sing using a vocal organ called a syrinx, which dinosaurs may not have had. So that iconic Jurassic Park scream, amazing for suspense. Probably not what a real dino sounded like. But guess what? The real soundscape might have been even wilder. Science is constantly rewriting the dinosaur portrait. They weren't just movie monsters or museum skeletons. They were warm, fuzzy, clever, sometimes even colorful animals. Part reptile, part bird. 100% fascinating. And for all we've learned, for every fossil, cladogram and CT scan, so many questions still remain. How did feathers evolve into flight? How did dinosaurs communicate? Were some of them even smarter than we give them credit for? These aren't questions of fiction. They're scientific frontiers. One fossil, one feather, one footprint at a time, and the story is still unfolding. Feathers were only the beginning, because in the next chapter, we look beyond skin and scales into social lives, intelligence, migration, parenting, memory. Were dinosaurs just primitive creatures, or were they far more mentally complex than we've imagined? Chapter 7 might just surprise you. Chapter 7, Dinosaur Behavior and Intelligence. When you think of dinosaurs, intelligence isn't usually the first word that comes to mind. You think teeth, claws, size, maybe a tail that could flatten a car. But what if we've been underestimating them? What if dinosaur brains weren't as tiny as we once thought? Or more importantly, what if they were way smarter than their body size suggests? In this chapter, we're stepping out of the shadow of the Colossus and into its mind, exploring behaviors, social structures, instincts, and maybe even emotions from a group of creatures long thought to be little more than primal. Let's rethink the way these ancient animals may have lived, not just biologically, but mentally. First, let's talk about a concept that gets tossed around a lot: EQ, or encephalization quotient. It's a rough estimate that compares an animal's brain size to what you'd expect for a creature of its size. It's not perfect, but it gives us a decent peek into comparative intelligence. Using EQ, scientists estimate that most big herbivores, like sauropods, didn't invest too much in brain tissue. Their EQs are low. In plain terms, forgive them, they likely weren't the philosophers of the Mesozoic. But certain groups, especially theropods and most of all the feathered ones, were a different story. Take Troodon, for example. Its EQ was off the charts for a dinosaur. Some scientists have gone so far as to claim it may have functioned on a level comparable to early birds or mammals. Its eyes were huge, perfect for night vision. Its brain case was large, its senses sharp. Did it solve problems, use clever hunting tactics, recognize patterns, maybe even remember territory? Very possible. And here's the catch: it wasn't alone. Dromaeosaurs, ornithopods, and even hadrosaurs show signs of engaging with the world in ways that hint at cognition far deeper than we once gave them credit for. Language? Maybe not. Emotion? Not likely in the human sense. But intelligence? Absolutely. In many forms. You can tell a lot about an animal, not by its roar or pose, but by its footprints. Fossilized dinosaur tracks, known as ichnites, offer something bones alone can tee, a snapshot of behavior as it happened. And guess what they reveal? Patterns. Groups of the same species moving together, tracks of young individuals alongside adults. Dinosaurs turning, stopping, even repeating paths across seasons, similar to how modern elephants or wildebeests migrate. In some sites, dozens of hadrosaur tracks follow winding paths together. Further evidence suggests that some ceratopsians also moved in herds, not just for safety, but perhaps for social cohesion. This kind of coordinated movement suggests decision-making, leadership, and even memory. Migratory patterns echo modern birds and mammals, which remember grasslands, nesting sites, and rutting grounds. Were there dino herd leaders, scouts, coordinated movement to avoid predators? The ground beneath their feet seems to whisper, yes, something was going on here. If intelligence is partially measured by complexity of behavior, parenting might be the gold standard. And dinosaurs, remarkably, gave the world its first real glimpse into devoted parenting in the fossil record. Let's talk about Maiasaura. The name literally means good mother lizard. Why? Because scientists discovered fossil nesting grounds in Montana with unmistakable signs of care, broken eggshells, growth stage fossils, and repeated nesting in the same locations over what seems to be many years. Some nests even showed that the hatchlings stayed in the nest beyond hatching age, meaning they were likely fed, protected, and tended to by adults. That's a level of commitment we associate today with birds and mammals, not ancient reptiles. Even oviraptors, previously accused of stealing eggs, were found brooding atop nests in very bird-like positions. The evidence now shows oviraptors were likely protective parents, not thieves. This changes so much. It hints at social bonds, future planning, even generational knowledge transfer, at least in some form. Let that sink in. Dinosaurs had nurseries. No smartphones, no language, no facial expressions. So how did dinosaurs communicate? They used what they had, and they built it into their bodies. Take the elaborate horns and frills of ceratopsians or the crests of hadrosaurs like Parasaurolophus. At first, these structures seemed like random ornamentation, but modern research suggests many of them had practical roles in communication. That dramatic curved tube on Parasaurolophus, it may have functioned like a resonating chamber, producing deep, foghorn-like calls that could be heard over miles of dense vegetation. Perfect for warning others, signaling mating status, or coordinating migrations. Others, like the bony head domes of pachycephalosaurs, may have engaged in ritualistic headbutting, much like mountain goats or rams today. Not just mindless bashing, but social displays with clear pecking orders. Visual cues mattered too. Vibrant feathers, moving tails, raised frills. They could all send messages. We're only scratching the surface, but here's what's clear. Dinosaurs didn't grunt and stumble through life. They called, signaled, and interacted in ways utterly familiar, if you know what to look for. Okay, let's have a little fun here. We know reptiles today can learn. Even crocodiles and monitor lizards show surprising intelligence for cold-blooded creatures. Birds, descendants of dinosaurs, can recognize faces, solve puzzles, and mimic speech. So what about dinosaurs? We don't have a recorded dino solving a Rubik's Cube, tragically, but we do see hints of problem-solving behavior inferred from anatomy and ecological interactions. Raptors especially, with grasping hands, sharp vision, and strong memory processing structures, likely figured things out. Coordinated hunting, a kind of basic strategy. Chances are we'll never fully decode that, but it's impossible to ignore the mosaic of clues. Social nesting behavior, coordinated herd movements, specialist feeding strategies, sophisticated signal structures, evidence of courtship and display, predator evasion techniques, possible pack hunting in some theropods. At some point, this stops feeling like accident or instinct and starts looking like complex behavior with purpose. Is that intelligence? Maybe not by human standards, but certainly by nature's standards. And just for fun. Recent findings even suggest that some dinosaurs engaged in play. Like young birds today, they may have run, pounced, or tested each other's reflexes, not just for survival, but for fun. That's not just instinct. That's personality. Dinosaurs, it turns out, weren't just thunderous engines of destruction. They were curious, protective, social, adaptive, and sometimes, perhaps even creative. They raised young, they navigated harsh climates, they migrated, they evolved tools for sound, sight, and touch. They remembered, they responded. And the best part? We're still learning. With every nesting site, every trackway, every bone dug from quiet stone, we get a little closer, not just to what dinosaurs were, but how they lived. Brains, not just brawn. Feeling, not just fighting. Behavior, not just biology. But now it's time for a turning point, the most cataclysmic event in Earth's prehistory. In the next chapter, everything changes. In mere moments, an age ends. What exactly happened? And how do we know? Chapter 8 takes us face to face with the asteroid that rewrote life on Earth. Chapter 8, The Asteroid and the End. For over 160 million years, dinosaurs ruled the Earth. They outlasted supercontinents, ice and fire, mass extinctions, and countless other species. They were unstoppable. But then, in the blink of an eye, everything changed. It was a peaceful day. Late Cretaceous Earth was warm, green, vibrant with life. Herds of triceratops grazed lazily. Flashes of color flitted through trees, not birds but feathered dinosaurs. T-Rex, the apex predator, reigned confidently in the forests of North America. And then, from the sky, a streak of light and silence. The asteroid didn't roar, not at first. It moved too fast. Faster than sound, faster than comprehension. In less than a second, it struck. And when it did, the world ended. Let's get one thing clear. This wasn't just a big rock. It was a 6-mile-wide asteroid traveling over 40,000 cm. When it slammed into what is now the Yucatan Peninsula in Mexico, specifically the spot now marked by the Chicxulub crater, the energy released was more than 1 billion atomic bombs. The impact carved a crater over 110 miles wide and kicked up superheated debris into the atmosphere. Within minutes, earthquakes shook the land. Tsunamis taller than city buildings crashed inland. A global firestorm ignited as molten fragments rained down, setting forests ablaze. Then came the darkness. Dust, ash, and sulfur from vaporized rock filled the atmosphere, blocking out sunlight across the globe. Photosynthesis stopped, temperatures plummeted, food chains collapsed. In a matter of weeks, coastal species died. Within months, ecosystems crumbled, and over the next several thousand years, 3/4 of life on Earth vanished. Far beyond the horror of impact, it was the after effects that did the real killing. It sounds like a scene out of science fiction, so how exactly do we know all this happened? Turns out the clues are everywhere, if you know where to look. In the 1980s, scientist Luis Alvarez and his son Walter discovered a curious thin layer of iridium-rich clay in rock strata across the globe. Iridium is rare on Earth's surface, but abundant in asteroids. This layer appeared right at the geologic boundary between the Cretaceous and the Paleogene period, what used to be called the KT boundary, now KPG, 66 million years ago. And that same line? It's found all over the world, across every continent. Then in the 1990s, the Chicxulub crater was finally confirmed beneath Mexico. Seismological data and deep drilling cores sealed the deal. All signs pointed to a single global-scale catastrophe. And the fossils? They stop almost immediately above that line. Below it, T-Rex, Triceratops, Edmontosaurus. Above it, nothing. The dinosaurs, the non-avian ones at least, were gone. Was it just the asteroid? Or were the dinosaurs already on the ropes? That's something paleontologists still debate today. Leading up to the impact, Earth was undergoing volcanic upheaval, especially in what is now India, where the Deccan Traps, massive lava flows, were erupting for thousands of years. This would have warmed the climate, released greenhouse gases and stressed ecosystems long before the asteroid hit. And marine ecosystems. They were already seeing losses. Species diversity was shrinking. It's possible that Earth was already in decline until the asteroid finished the job. Most scientists agree, even if the world was unraveling slowly, it was still habitable. The asteroid didn't just speed up the collapse, it made recovery impossible. So who exactly didn't make it through the apocalypse? Gone. All non-avian dinosaurs? Pterosaurs? The flying reptiles? Marine reptiles like mosasaurs and plesiosaurs? Roughly 75% of all plant and animal species on Earth. But tucked within the wreckage of mass extinction were the improbable survivors. Crocodilians with their flexible metabolism, aquatic lifestyle, and burrowing behavior. Turtles safely hidden beneath mud and water. Mammals, small and adaptable, some of which may have even burrowed underground during the worst phases. Ferns, springing up rapidly in the post-impact fern spike that shows up in the fossil record. And, of course, birds. Yes, birds. Those small, feathered, warm-blooded animals that had evolved from certain theropods survived. Why? Possibly due to flight, allowing quicker escapes, small size, requiring fewer resources, flexible diets, even eating seeds and insects, possible nesting in tree cavities or remote shelters. Whatever the reason, these avian dinosaurs endured, and from them, eventually, came every bird alive today. A living echo of the age that ended in fire and ash. Picture it, a quiet forest, weeks after impact. The skies are darker than night. Ash rains down like snow. The air smells like sulfur and rot. And there's silence. No roars, no swarms, no songs. Only the survivors remain. Tiny mammals scurrying for whatever food they can find, birds flying low, navigating dim, choking skies. Small reptiles hiding in cracks, insects gnawing at what's left. It's a new world, empty, broken, but not defeated. In the decades to follow, the fog begins to lift. Sunlight returns, ferns re-emerge, new ecosystems start clawing back into existence, and into that chaos step the mammals, ancestors of bats, whales, rodents, and eventually humans. But that's only possible because the dinosaurs had left the stage. Let that sink in. Had the asteroid missed Earth by just a few hours, the entire timeline of life as we know it could have been rewritten. And we, humans, might never have had a chance at all. An ending that feels too cruel for creatures so magnificent, but also strangely poetic, because extinction in nature is not the end of life. It's a transformation, a handing of the torch. The dinosaurs weren't failures. They were survivors, explorers, experimenters, and they ruled the Earth unimaginably longer than our own species has even existed. And you want the real twist? Some of them never left. The next time you look out your window and see a pigeon strut across the sidewalk or hear a hawk's cry echo on the wind, don't just think bird, think descendant of the dinosaurs, because they never went completely extinct. They just changed shape. Up next, we turn our attention to the evidence left behind. What survives when the world ends? Bones, fossils, trace impressions of the past. In Chapter 9, we explore how paleontologists read the Earth's memory, from ancient bones to chance discoveries, and how we've pieced together the greatest story never told. Until now. Chapter 9, Fossilization and Finding the Past. Have you ever held a fossil in your hand? A real one. There's something oddly electric about it, the sense of touching time, of connecting with something once alive, now turned to stone. It's part magic, part science, and completely awe-inspiring. But here's the truth. Fossils aren't just cool souvenirs or museum centerpieces. They're messages. From a world no human ever saw, sent across millions and millions of years, waiting for someone, maybe someone like you, to find them. This is the story of how we find them, how they form, and what they tell us about the creatures that once ruled the world. Let's start with something wild. Over 99.9% of all living things never become fossils. That's right. Most life disappears without a trace, eaten, decomposed, scattered by wind and water. So how do the lucky few make it into the fossil record? Here's the recipe. 1. Die in the right place, usually near water, rivers, floodplains, or lakes. The faster you get buried by sediments like mud or silt, the better. Exposure is the enemy. Predators, bacteria, weather, all of it chews away at remains. 2. Stay buried. Over time, layers of sediment build up above the buried remains. Pressure increases, heat builds. Slowly, minerals seep into the bones, replacing organic material atom by atom. 3. Turn to stone. Eventually, those bones aren't bones anymore. They're rock in the exact shape of what was once there. Petrification complete. 4. Get discovered, maybe. After millions of years, erosion, earthquakes, or a lucky human might finally expose your fossilized self to the surface again. The result? A 100-million-year-old leg bone sitting unassumingly in a rocky outcropping until a curious eye spots it. And the story begins again. Most people think of fossils as dinosaur skeletons, but the fossil record is full of surprises. Trace fossils. These include footprints, nests, burrows, or even those incredible fossilized dino poop samples, called coprolites. They don't show the body, they show behavior. Imprints. When soft tissues leave impressions in sediment, think scales, feathers, skin, even eye ridges or belly lines. Mummified fossils. In rare cases, everything dries out before decomposition sets in, preserving skin, tendons, and internal organs. These are literal time capsules. Resin fossils. Ever heard of amber? Fossilized tree sap that sometimes traps insects or feathers mid-flight. Jurassic Park was onto something here, just minus the cloning. The variety is staggering, and each fossil type gives us a different volume of the story. A skeleton tells what it was, a footprint tells how it moved, A crop light tells what it ate, and together, they restore an entire world. Here's the not-so-secret truth of archaeology and paleontology. Where is everything? Some locations are fossil gold mines. Why? Because the conditions for fossilization were just right. Let's look at a few. Hell Creek Formation, Montana, USA, home of the iconic T-Rex and Triceratops, final stage of the dinosaurs before the asteroid struck. Every inch of soil here is a time machine. Morrison Formation, Western U.S. Jurassic Central. Stegosaurus, Allosaurus, and Diplodocus walked this ancient savanna. Liaoning Province, China. Possibly the most important fossil site of the 20th century. It's where the feathery revolution began, yielding startlingly well-preserved fossils complete with feathers, colors, and even internal organs. Patagonia, Argentina. Giant country. This is where we found some of the largest dinosaurs ever, including Argentinosaurus and Giganotosaurus. Isle of Wight, UK. Sometimes called Dinosaur Island, it's one of the most prolific dino sites in Europe. And yes, we've found fossils on all 7 continents, even Antarctica. A reminder that the world was once very different, warmer, wetter, wilder. It's not just about digging, it's about reading geography like a map to the past. Desert cliffs, riverbanks, Arctic mountains, they're all time portals, waiting. You'd think dinosaur fossils are only discovered by lab coat-clad experts in remote deserts, but some of the world's biggest discoveries were made by farmers, kids, dog walkers, even people taking shortcuts in mines. Take Mary Anning, a child from England's coast in the 1800s. At just 12 years old, she found the first complete ichthyosaur skeleton ever discovered. She taught herself anatomy, sketching, and geology, and rewrote natural history, without ever receiving the respect she deserved during her lifetime. Or Jack Horner, the real-life inspiration for Jurassic Park's Dr. Alan Grant, who started out as dyslexic, flunked out of college but eventually discovered the first evidence of dinosaur parental care while working a dig in Montana. And even recently, in 2020, a 4-year-old in the UK found a fully intact dinosaur footprint while walking with her family along the beach. Legit. The truth is, if you're curious, respectful, and patient, you can be part of this too. Fossils aren't locked away, they're hidden everywhere, waiting. So we find these fragments, these bones and teeth and impressions. What can we actually learn from them? Turns out, almost everything. Bones tell us about species, posture, health, even age. Bone microstructure can show growth rates, telling us how fast a dino matured. Pathologies, healed injuries, bone deformities, hint at life stories and survival. Teeth-dong diet. Sharp teeth, carnivore. Flat grinding plates, herbivore. Both, omnivore. Coprolites and stomach stones, called gastroliths, explain digestion. Trackways offer social patterns, speed estimates, and sometimes predator-prey interactions in real time. And the crazy part? We're getting more advanced by the year. New technologies like CT scanning to look inside fossil skulls and project brain size. Isotope analysis to estimate what the animals were eating and where. 3D printing to recreate bones and understand how muscles attached and moved. Paleontology today is like detective work, armed with lasers and supercomputers, and still, we've only scratched the surface. Some experts believe we've discovered less than 10% of all dinosaur species. Let that sink in. The past isn't complete, it's being written right now. Fossils are more than rocks. They are stories in stone. They tell us how Earth changed, how life adapted, how extinction reshaped the course of history. They connect us to creatures whose lives ended millions of years ago, but still leave prints under our feet. Even now, some of the greatest dino discoveries in history are probably still out there, just beneath the surface, waiting for storm erosion, a shovel, or a lucky footstep to bring them into the light. Because the story of the dinosaurs didn't end with the asteroid. It continues in chapter after chapter, deep beneath the Earth, which brings us to the final installment of this incredible journey. Because believe it or not, dinosaurs never really left us at all. In Chapter 10, we explore the living legacy of dinosaurs, how they shaped evolution, culture, and even you. Chapter 10, Legacy of the Dinosaurs. Close your eyes and imagine a dinosaur. Go ahead. Maybe you picture a towering T-Rex, muscles rippling under scaly skin, or a horned Triceratops, eyes fierce but thoughtful. Maybe you see a gliding pterosaur, or a giant Brachiosaurus casting a shadow across a flooded plain. Now open your eyes, look out your window. See that crow hopping down the sidewalk? Or that pigeon puffing its chest like it owns your balcony? Yep, dinosaurs. You're living in their age right now, just not the way you'd expect. Let's talk about how dinosaurs never truly disappeared, how they've shaped everything from evolution to ecosystems, to movies, music, and memes. Because their legacy didn't end with a crater, it just changed shape. Let's start with the obvious. Birds are dinosaurs. We've said it before, but at this point it bears repeating. Biologically, a sparrow is more closely related to a velociraptor than a velociraptor was to a T-Rex. From feathers and hollow bones to nesting behavior and three-toed feet, the blueprint never left. It just got lighter, more aerodynamic, and eventually airborne. Some birds even retain vestigial claws or teeth-like structures in early development. And the wishbone, the furcula, a feature thought unique to birds for decades, theropods had it too. In fact, modern birds are classified as avian dinosaurs, which makes every single robin, raven, hawk, and hummingbird both a marvel of evolution and a living fossil. So when we say dinosaurs are extinct, technically wrong. They're just singing now. But the legacy goes even deeper than that. Dinosaurs didn't just survive through birds, they reshaped the evolutionary fabric of Earth. Their dominance for 160+ million years kept mammals small, nocturnal, and clever. So when the asteroid wiped out the giants, the surviving mammals were already perfectly engineered to rise in the aftermath. In a strange way, we may owe our own existence to dinosaurs having ruled first. Their scene-stealing role in Earth's biological theater created the very conditions mammals needed to thrive once the curtain fell. And the environments they helped build, vast grazing plains fertilized by migrating herds, ecosystems structured around predation, nest-based parenting developed and passed down, rippled forward into the age of mammals. Remove the dinosaurs from Earth's story, and the whole plot changes, forever. There's something about dinosaurs that digs deep into the human psyche. Kids can name more dinosaur species than state capitals. We wear them on t-shirts, design them into sports mascots, watch them terrorize theme parks in billion-dollar movies. Why? Because dinosaurs hit that perfect nerve, that emotional collision between fact and fantasy. They're real, yet they feel unreal. Powerful, yet long gone. Familiar, but impossibly alien. They remind us how old the world truly is. They remind us how fragile life can be. And they give us a kind of imaginative bravery. The thrill of standing, even just in our minds, next to something that would dwarf us in height, weight, and raw evolutionary success. Dinosaurs were part of the first sparks of curiosity that pushed humans toward modern science. They still are. Here's the wild part. Dinosaur science is exploding faster than ever. Right now, we're in what paleontologists call a golden age of discovery. On average, we're identifying a new species of dinosaur every 2 to 3 weeks. That's not a typo. From tiny bird-like gliders unearthed in China, to massive armored species hiding in South American cliffs, to entire ecosystems found below Antarctic ice, there is so much more to learn. And with new technology, we're not limited to digging up bones. We're scanning fossils in 3D to analyze joint movement, studying melanosomes to reconstruct feather color, using isotope chemistry to understand how dinosaurs migrated, even recreating muscles and ligaments digitally in full-body motion models. Not only can we now see these animals better, we can simulate how they breathed, hunted, fought, nested, and evolved. The final thrilling twist. Some scientists believe that soft tissues, including proteins and blood vessels, may even survive in very rare fossilized remains. Are we close to cloning dinosaurs? No. But are we close to understanding them as real, living, breathing beings? Closer than ever. At the end of it all, you might ask, why care? Why should it matter what happened to giant lizards 66 million years ago? Here's the answer. Because the story of the dinosaurs is the story of change, of how life adapts, evolves, rises, and eventually ends. It reminds us that no species is permanent, not even ones that lasted hundreds of millions of years. It reminds us to look at the Earth, its climate, its creatures, its balance, with humility and care. It tells us that invention is possible, that nature always moves forward. And it gives us one more reason to look at the world with wonder, to stand beneath a museum skeleton and feel something primal click into place, to find a fossil and realize you're the first human to ever see that creature's remains since it walked the Earth. Dinosaurs aren't gone. They live in our skies, they live in our labs, and most of all, they live in us. In awe, in curiosity, and in every story we tell about life. Final thought. If time is a book, the dinosaurs got a chapter longer than any other, and it was epic. But what's most amazing, it hasn't ended yet. They still soar above us, still whisper through bone and stone, still live on in every child who draws a stegosaurus, every paleontologist brushing away dust, and every curious mind that simply asks, what came before us? Dinosaurs ruled the Earth once. In some ways, they still do.